Alright, so your project is microscopy nuclei segmentation. The overall goal of this project essentially is to take a simple microscopy nuclei image and then automate the process of segmentation using deep learning. So in this project, we're providing a simple web platform that automates that for us. So in a regular sense, what scientists slash biologists do in their labs is they take these images under a microscope and then on their computer system they manually map the area of the nucleus in the cells that are shown or in that segment of tissue or whatever that they have sampled through their microscope, and then go through this gruesome process of trying to mark each and clean it up so that they can use it for analysis later on. As seen or as I've explained it so far, it seems like a very hard and troublesome thing to do. So with deep learning, we can actually make this easier and a lot more uh, less, or let's say no labor at all in the process of trying to get this. The proposed system that we have right now basically takes an image that the scientists will upload, which they will take to their microscope as usual, and the system will then feed it to the required neural networks and generate the expected output, as shown here by this image of an example. So what you're seeing now is the main web application. It has a few segments which talk about the application essentially, but we'll just jump into how it works. So you can jump into the segmentation part by either clicking on try it out or perform segmentation. Let's start by clicking on try it out. So when you go to this section, it asks you to upload a image file. This image file represents the image that is taken by the biologist under their microscope. Let's take an example file. Give me a sec. So what we'll do is we'll jump into the required folder. Yeah, images for testing. We'll take one of these images. Cool. Now you click on process. Process will send an API call to the backend system, which will feed it through the neural network systems. So we have an ensembled model of a unit and a mask RCNN. So we'll just run this through. Once you run it, it'll take some time to load. Then you get this image, this the output image that is generated. Seems very simple. Let's jump into the model section, which will describe about how a system works. So we have an ensembled unit and mask RCNN, which are both state-of-the-art in the field of image segmentation. So what happens is when you make a back call to the backend, we feed both these images to the respective models and then get the output that they have generated and then use ensembling approach to figure out what to use essentially. So in the how it works section, we describe about how the system works with an architecture diagram. Basically, you access the platform, upload the nuclei images. The web platform site internally connects or interacts with the machine learning model that is being run. So we send the image that is to be segmented to nuclei. The machine learning model takes that image, processes it, and then sends us back the segmented nuclei images, which is then sent back to the user, which is you usually. In the references section, we referenced all the other papers slash approaches that we've taken inspiration from. Fairly simple. Now, how does the work button also takes you to the how it works section. Alright, now let's talk a little about the code. So we define essentially a endpoint called process, which is handling all our API calls for the models. Then we have a index route endpoint, which is handling the main index page route. So let's just jump into index.html to get a feel for what it means to be on the home page. On the home page, we have a very simple setup. we are using Bulma CSS framework. So it's a very simple CSS framework, not as bloated as Bootstrap, but very light or to the point, makes it easier for us to design. Then we have something called as Font Awesome. Font Awesome is used to add the icons on the page and certain specific aspects of the system. Then we have a font called Merriweather. This font is the main font which is used in your h1 tags, h2 tags, and other header tags. Then we have a custom style sheet that I've taken from another uh, system that we have seen, which basically provides us with the uh, movement feel when you're shifting between different divisions for the first time. Now jumping into the core HTML, we have a very simple nav bar with project demo, the nav items, which is perform segmentation models, how it works, and references. We have a main hero body, which basically shows the title of the project, description, and all the other buttons that we have right here. We'll just scroll this part. This is the perform segmentation part. In the perform segmentation part, we have a simple title, a description for that, and a button to choose your file. So after that, we have a division called output. This div tag essentially is used to store slash hold the image output that we get from the API endpoint to which we make the request. You can also see something called as a progress tag. This is not shown when you load the website, but it's always running. So when you make a request, this is what we show you. Now let's just jump right to the bottom. There's a lot of formatting in between. I believe those are pretty simple. We can just jump down into the main core JavaScript. JavaScript right here, as you can see, essentially is we have a single function which is to handle clicks on the process button. So when you click on the process button, we first get the file name, get the form data, we basically just say show the progress bar, hide the output section, add the file to the form data, and then make an AJAX request. So the AJAX request is a post request that is made to the process endpoint, and we give it the file data that is required to be sent. Line 332, we ask it to hide the progress bar when we have a success request. So you have two types of outputs. You have a success or an error. A success is when you get a valid response from the API endpoint. An error is when you get a invalid response. An invalid response may be something like a 500 internal server error code, or any other thing that is not considered 200-300 range of HTTP codes. In the case that we get a success, we basically take the output and we ask it to map it to the image or add an image whose source is the URL provided by the backend, and then we show the output after 2 seconds of animation. In the case that we have an error, we show a h3 tag which says server error, and we show it after 2 seconds of animation, and we log this output regardless. Now jumping into the app. The app fairly is simple. Let's just jump into the process endpoint. We got the index. In the process endpoint, we are saying that it only handles post requests. In line 15, we say that we wanted to collect the file data from the post request, given that we can access it. So we have given it the name origin name in the index, if you remember. So we are accessing that same thing. Then we go and save that file into the uploads directory, which is in the same folder as the project. Later, we define the image width and height 256 across 256, because that is the size of the image that the model that we're building expects. Then we load that image by setting a resize or slash target size that we want it to be in. Given that the image that comes out isn't in the specific format that it needs to be for the model, we first convert it into a numpy array. After that, we then expand its dimensions so that it can be given as a four-dimensional image. Four-dimensional because the first index is essentially used to define the nth image. In our case, there's only one image, so we had to just expand it once so that the model can handle it. Next, what we'll be doing here is, given that we have two models that we need to make predictions from, we will basically call the predict function of each of these models. So we have the first model, which is our unit model. Then we have the second model, which is our mask our CNN model. So this is where we make the predictions on the image that we have modified for the expanded dimensions. Now that we have done that, we need to basically weigh in and see what prediction is better than the other. So we do a simple vote type approach where we compare the probabilities that are given in the prediction versus the other prediction and see if one prediction has all the values greater than or mostly greater than the other prediction. After that is done, based on the result of this, we either select the first prediction or the second prediction. Once we have decided on the final prediction, what we do is we need to store that prediction, because if we were to send the image data, that would not be one easier for the front end to process, and two, security wise isn't a great idea. So what we do is we store that image or the prediction image locally in the static folder. Afterwards, we use matplotlib's imsave function to save that prediction in the prediction file with the squeezed prediction. The reason why we do mp squeeze is because this image is on 4 dimensions, or we believe 3 dimensions either. In that case, we do not want it to be that way. We want it to be put on a single 2 dimensional image. The output essentially has to be given in the form of a reasonable format. So ideally the output is in grayscale, but with matplotlib it has its function which will adjust the formatting to make the highlights more visible, which is why we do matplotlib's imsave. After which we return the URL to the file of the prediction saved in the static output folder. Alternatively, if it doesn't work, or if it's not able to access that file name, then we return doesn't work, which in case is usually handled in the success category, but you see a different output for that. Moving on to the model. So we have a very simple unit model. Basically, this is a one-to-one, I believe, of the unit model as described in the research paper. So we have a simple class called the segmentation model. It has an init method which defines the height, width, channels, and the summary of a model. Then you have a method called create underscore model, which generally creates the model of the unit architecture. Afterwards, it returns that same model. It is only returning the structural implementation of the model and not the compiled model. There's a slight difference in that. So you can see that we have a helper function right here. So we have two helper functions. One is to add lines to the summary, other is to reset the model summary. Next, we have a function called generate model summary. The goal of this function essentially is to generate the model summary, as it says. So model summary describes the layers and the how uh, these layers are connected with each other, and usually it is printed out to the screen. So the goal essentially here is to redirect the std out into a lambda function, which instead adds that line into the overall global model summary. Next, we have a function for training as well. It takes in a few parameters. Xtrain is the training variables that we want to train on. In this case, it's going to be the image data. Then we have ytrain. Ytrain is the image output that we expect from the model. Then we have a few callbacks. Callbacks are methods slash end checkpoints or things like that are called during the training process of the model. Then we have a validation split. This dictates essentially how we want to split our training data in the form of training slash validation. Point one means we have 90% training and 10% validation. Batch size indicates essentially how many images that we want to train parallelly on the model. Epochs represents how many iterations that we want to essentially go through. 50 is a decent amount for a deep learning model which has batch size 32. Moving on to the test method. The test method essentially is to test each and every single function of the model which comes under segmentation model. So the file structure of this project essentially was slightly different before it was packaged and given to you, which is visible when you look at mask RCNN model. Mask RCNN model was originally in a separate folder called mask RCNN, which is why the import on line 17 says so. But you can just but this is fine as we are using the saved model files rather than using the runnable model live. So mask RCNN model right here basically describes the mask RCNN model and has a bunch of functions which are required to help and use it. So I've put a lot of documentation into explaining what each of these methods already do and what they're supposed to do. And some of the places have references. These references are mapped to the papers or inspiration code examples that are taken from for the implementation of the mask RCNN. This is a very low level slash one-to-one mapping implementation. Now, to talk about the files, you can see here in app.py we have two functions which are loading the models. One is a saved model hy, which is a unit model, and the other is the mask RCNN. So we have these two lines. What are they supposed to do? Right? These are actually loading the model structure along with the weights, which are saved in these files respectively. So why do we use the hy format? We use the hy format because it allows us to both encapsulate the structure of the model and the data slash the weights required to use the model. So by this, we don't have to use the classes that were defined, but we can retain the structural integrity. And that is all for the code explanation. There's also a research IPython notebook which you can go through, which is me basically trying to figure out how to set up and slash use these models. Thank you.